So, today we are talking about site investigation. So, let's see. Site investigation, interpretation of topographic map, aerial photograph, geological map, engineering geological map, geophysical methods, direct exploration method. Map, the presentation of three-dimensional geographic objects or features in two-dimensional plane in a reduced form. The general configuration of a land surface, including its relief and the position of its natural and man-made features, is called topography. The map representing the map representing topographic features by means of contour lines are called topographic maps. A topographic map is a line and a symbol representation of natural and selected man-made features of a part of the earth's surface plotted to a definite scale. A distinguishing characteristics of a topographic map is a portrayal of the shape and elevation of terrain by contour lines. Topographic maps. Topographic maps are the orthographic projections of the terrain and are prepared with the help of aerial photographs. The projection of an object or feature to the plane parallel to the plane where the object is lying is called of orthographic projection. Straight and vertical lines from different points of the object are drawn between these planes, thereby projecting the real shape and size of the object. The map shows selected man-made and natural features, vegetation, relief, roads, drainage, temples, school, transmission line, etc. Scale, the ratio of dimension of an object in reality to that in a map. If an object having a length of 250 meter, that is 25,000 centimeter, for example, is represented by 1 centimeter on a map, the scale is 1 is to 25,000. Usually, topographical maps are prepared in the scale of 1 is to 1 million, 1 is to 5 lakh, 1 is to 1 lakh 25,000, 1 is to 1 lakh, 1 is to 50,000, 1 is to 25,000, and 1 is to 10,000. The scale of the topographic map varies according its use. The advantage of a graphical scale over a numeric scale is that the information is not changed when the map is enlarged or reduced, as the geographical scale presented on a map is also resized accordingly. The signs or signals used in a map to provide various pieces of information are known as symbols. The usual symbols used in a topographical map are of buildings, schools, post office, village, trail, roads, rivers, forests, landslide area, etc. In a topographic map, the symbols are drawn in the map and their explanation are given outside the margin, and it is Tom legend. Contour, imaginary lines joining the points of equal elevation in a map. The vertical distance between any two consecutive contours is called contour interval. The contour interval is kept constant for a contour plan, or information may be misleading. The distance between two adjacent contours depends upon the steepness of the ground. The choice of proper contour interval depends upon nature of the ground, scale of the map, nature of the ground, the terrain being represented in the topographic map could be flat or steep. If the area is flat, the contour intervals are less as the contours are seen far from each other. If the area has a very steep slopes, greater contour interval will be appropriate, or the contours will be very close to each other. Scale of the map. The contour intervals will be inversely proportional to the scale of the map. Greater contour intervals are required for the maps of small scale and vice versa. Purpose and extent of survey. For detailed design, the map will be of large scale, hence the contour interval must be of a small interval. The extent of survey will generally be small. Time and expense. For smaller contour interval, more time and expense is required, as survey must be detailed and accurate. If time available is limited, greater contour interval is generally used. Considering these factors, a fixed contour interval is chosen and is kept constant throughout the map. Characteristics of contour lines. Two contour lines of different elevations cannot cross each other. Contour lines of different elevations can unite to form one line, one only in the case of vertical cliff. Contour lines close together indicate steep slope. They indicate a gentle slope if they are far apart. So here is a figure of steep slope contour. Contour in steep slope, contour in gentle slope, and contour in very gentle slope. A series of straight, parallel, and equally spaced contours represents a plane surface. Two contour lines having the same elevation cannot unite and continue as one line. Similarly, a single contour cannot split into two lines. A contour line must close upon itself, though not necessarily within the limits of the map. A closed contour line with one or more higher ones inside it represents a hill. Similarly, a closed contour line with one or more lower ones inside it indicates a depression without an outlet. Contours form curves of U shape with the convex side of the curve towards the lower ground in case of spur. Contour lines cross a valley line at right angles. They form sharp curves of P shape across it with convex side of the curve toward higher ground. In overhanging cliffs, the contours of lower elevation will be seen in a dotted line crossing the higher contour. Uses of topographic map. Drawing of sections. To know a general shape of a ground, a cross section can be drawn from the help of contours in the topographic map. Tracing of contour, gradient, and location of a route. For drawing a route for a road, railway, canal, or transmission line, the contour plan is very much important. It gives the information about the terrain and helps to know the tentative steepness of the route being drawn. Measurement of drainage area. A drainage area for a point is the area which is the source of all water that pass through the point. A contour map is used to trace the line separating the basin from rest of the area. Calculation of reservoir capacity. The topographic map will be helpful in calculation of reservoir capacity. The volume of water between any two contours will be approximately equal to the average area between the two contours multiplied by the contour interval. Aerial photography. An aerial photograph or air photo is a pictorial representation of a portion of the earth's surface taken from the air. View by human eye, photograph perspective. Map. Orthogonal projection. Vertical aerial photograph. The axis of the camera is vertical or nearly so. Oblique photograph. The axis is more or less inclined. High oblique photographs include the horizon. Low oblique do not. Don't. The vertical photograph is used as a basis for topographical mapping, agricultural soil mapping, and geological interpretation. Air photo. Air photo survey. Air photo survey is very rapid in comparison to corresponding ground survey. Ground survey costs much and in most inaccessible places cannot be done at all. As the aerial cameras are mounted in the aircraft, the instability of the camera in the flight and possibly inaccuracy to determine the flight altitude correctly. The result of aerial survey are less accurate than the ground survey. Except in areas with dense forest cover which obscures the view, the air photo reveals every natural and man-made feature on the ground. Determining photo scale. Scale is equal to camera focal length f by flying height above terrain. That is s dash, where s dash is equal to aircraft flying height h minus terrain elevation h small h, capital H minus small h. Relief displacement. Objects will tend to lean outward. that is b radially displaced. The greater the object is from the principal point, the greater the radial displacement. Example, cooling towers towards the edge of the photo show greater radial displacement. Mosaics. A mosaic is a collection of photographs of a given area which are joined together to form a continuous overall photograph of that area. The photographs have 60% overlap between them. As the edges of the photographs are distorted, only the center part of the photographs are used. For the planning of large structure, it usually is necessary to make a mosaic, as one photograph rarely covers the entire structural area. Useful for laying out railways, highways, canals, transmission lines, and as base sheet for geological map. Air photo interpretation. When a scene is being viewed through an aerial photo, there is an immediate feeling of naturalness. Aerial photographs are the base for topographic map. Aerial photographs do not suffer from problems of human error in the way that maps sometimes do. To identify objects on an air photo, following features of that objects are represented by its image should be given attention: shape, size, pattern, shadow, tone, texture, and relationship. Shape. Many man-made and natural features have distinct or characteristic shape and can be easily recognized, while some natural objects are hard to recognize. The size of objects can sometimes be identified by relating it to non-objects of photograph. Pattern. From peculiar arrangement of objects in photograph, it can be determined whether the object is natural or man-made. Shadows may help to determine the size and shape of objects. Relationship or association. Identification of one feature will help in identification of another object. For example, identification of cooling towers will help to identify the nuclear facility. Tone. Tone is the amount of light reflected by the object. In air photo, damp soil will have darker tone, whereas dry soil will look light. Texture. The frequency of tonal change within an image. It is the coarseness or smoothness caused by change in tone. Forest will look coarse, whereas grassland and water will look smooth. Uses of air photo. Geological information such as recognition of rock types and their distribution, recognition of bedding, faults, joints, which are very important to locate the engineering structures with high degree and feasibility. Study of landforms provide information on geological history of the earth. Drainage patterns. Tonal variation help to identify the lithology structure and their extinction. Erosional features like gullies and landslide and their extinct will tell about the slope geometry and the presence and absence of resistance and non-resistance rock. Geological map. A geological map is a special purpose map made to show geological features. Rock units or geological strata are shown by colors or symbols to indicate where they are exposed at the surface. Bedding planes and structural features such as faults, foliations are shown with strike and dip symbol. There are basically two types of geological maps: surface map and subsurface map. Surface geological maps are compiled from surface geological data. Subsurface geological maps are compiled from borings, well logs, geophysical surveys, and extrapolation of surveyed surface data. The amount of detail on a geological map depends upon the purpose of the map. Normally, a geological map contains information on the rock type, their mode of occurrence, grain size, color, and mineral constitution, the structure of rock, such as bedding, deep and strike of the beds, fractures, joints, etc., the depth and characteristics of overburden and wetter rock. For understanding the geological structure of a region, geological cross sections are constructed along a certain line. These sections represent the conditions which are to be found at depth, which are inferred from geology observed at the surface. Factors helping in construction of geological sections are contour lines, helping drawing topographic profile. Attitude of the strata beds. It is indicated by the component of deep computed along the line of cross section. Thickness of each rock unit may be obtained by boreholes or computed with the help of map scale and deep amount. Geological maps and sections illustrate the geological information in a concise form. The attitude of beddings, foliation, joints, falls, folds, etc. in the relation of slope, inclination, and direction has a great influence on the stability of slopes. Detailed geological map and engineering geological map provide valuable information for engineering purpose. The characteristics of rocks are the major importance in the selection of sites for infrastructures and their design. This diagram permits the engineer readily to ascertain the direction of most intensely joined rock in relation to its structure. These are the particular useful in design of tunnels, arc dams, and powerhouses. Engineering geological map contains the basic geological map on which all necessary engineering geological data. The rock type and the structure, joint patterns, rock stability condition, their relation with the slope, soil type, soil depth, their physical properties, landslide, slope, angle of an area. They also provide the information for engineering purposes like rate of weathering, strength of rock mass, seismic hazards, hydrogeological condition, etc. Engineering geological maps are prepared mainly for planning and civil engineering purposes. Engineering geological maps usually are produced on a scale of 1 is to 10,000 or larger scale. Information in physical properties of rock and soil are by visual observation, by in situ testing or sampling is necessary. If impossible to present in a single map, or series of overlays or an atlas of maps or attached engineering geological report may be prepared. Geophysical exploration investigation in which physical measurements are made at the ground surface by using special instruments to know subsurface information. They are useful in determining a variety of the physical properties of soil and rock. It is a blend of physics and geology. The physical measurements are interpreted in terms of subsurface geological condition, mainly perform for hydrogeological studies, hydrocarbon engineering, geological or geotechnical studies, geological mapping, archaeological investigation. These methods supplement data from surface mapping and shallow drill holes to provide a bridge between test data in the lab with real condition in the site. The most commonly used methods of geophysical methods are gravity method, magnetic method, electrical method, and Seismic method. The seismic refraction method is based on the variable transmission rate of seismic waves through metals of varying densities. The higher the elastic modulus of metal, higher will be the velocity of seismic waves. The velocity of the shock waves generally increase with depth below the surface, since the elastic moduli increase with depth. Seismic boundaries are distinguished by contrast in velocity between two media and can be refracts refract waves as well as reflect them. The seismic reflection method is the most extensively used in this technique. The depth of investigation is large compared with the distance from the shot to detector array. In seismic refraction, one ray approaches the interface between two rock types and the two rock types. If ray is passing from a low P0 to a high velocity P1 layer, it will be refracted and travel along the upper boundary layer of the P1 layer. This generates new disturbances along the boundary that travel upwards through the low velocity rock and eventually reach the surface. Limitations of seismic survey. Seismic determination are affected by noise, vibration, and therefore difficult to adapt in areas of heavy and fast traffic and near heavy machinery. When the underlying layer has low velocity, then the overlying strata, the seismic wave cannot penetrate, and it is difficult to get information below this layer. The surface distance needed for seismic reflection survey is roughly 3 to 5 times the depth of investigation for data collection. Electrical resistivity method. The geophysical survey which using the electrical and electromagnetic principle is the electric method. It is operated by ionic conductance of current through the Earth's metal and by the induction of current in metal by electromagnetic field. The electric method most commonly utilized for engineering projects involves the surface measurement of resistance of odd metal to control the current flow. It is based on the fact that variation in mineralogy that uh, that variation in mineralogy texture and content water determine the resistance of metal to current flow. Resistivity geological surveys measure variations in the electrical resistivity of the ground by applying small electric current across arrays of ground electrodes. The survey data is the survey data is processed to produce graphic depth sections of the thickness and resistivity of subsurface electrical layer. The electrodes supplying the current are termed the current electrode. Then the potential difference between two potential electrodes is measured. The engineering application of resistivity survey include measuring bedrock and water table depth, detecting solution features and voids, locating locating buried, locating buried alluvial channels, identifying fracture zones and discontinuities, mapping of leak at a contamination, defining saline groundwater incursions, finding abandoned mine shafts and working. Direct subsurface exploration. The geophysical methods are the indirect subsurface exploration, whereas the drilling, test pits, and boreholes are the direct subsurface exploration methods. Because of the difficulties of obtaining good quality samples of certain metals, such as sands and soft clays, for laboratory testing, some tests are considered best done in boreholes or samples in situ. Drilling. It can be carried out in soil as well as rock to find out the nature of the soil, rock, and their engineering quality. It also helps to determine the porosity and permeability of the soil, rock, and depth of the water table. The depth and location depends upon the geological condition and the rock and the type of project concerned. There are many. There are many methods. There are many methods of drilling into the surface, and each has its advantage as well as disadvantages. Cable tool or prescription drilling method. The hole is drilled by the impact and cutting action of the heavy sessile edged drilling tool that is alternately raised and dropped by the means of a cable attached. Can drill up to 80-60 centimeter in diameter, depth 600 meter. It is less effective in unconsolidated sand and gravel because the loose metal slumps and caves around the bit. Not applicable if undisturbed samples are to be obtained. Rotatory drilling. The bit rotates while cutting through the earth metal. Boreholes up to 45 centimeters in diameter. This method operates with a hollow rotating bit continuously cutting through the subsurface, and a mixture of clay and water or drilling mud is forced through the bit. The metal loosened by the bit is carried upward by the rising mud. The drilling fluid keeps circulating in and out of the drill and also helps to cool, clean the bit and preventing the well from collapsing. The bit used can be used. The bit used can be of diamond or titanium carbide or hydrogen steel. May be the only practical method to obtain undisturbed core samples, soil or rock. Agar boring. It is the simplest method of soil investigation and sampling. Depth of agur are limited by groundwater table and by amount and maximum size of gravels and pebbles as compared with size of the instrument. Agur cannot be employed in case of granular metal with large amount of rock with large amount of with large with large amount of rock chunks. Agur boring consists of driving a hand or power operated helical steel agur 5 to 15 centimeter into the ground and withdrawing it full of soil metal. Extension rods are employed for deeper penetration. This method is fast and economical for large to small holes. It is very suitable for soft to stiff cohesive soils and also can be used to determine groundwater table. Soil removed by this is disturbed, but it is better than wash boring, percussion or rotatory drilling. It is not suitable for hard or cemented soils, very soft soils, and also for fully saturated coastal soil. Standard penetration test (SPT). This this in situ this in situ testing of soil consists of driving a split spoon sampler with an outside diameter of 50 into the soil at the base of the borehole. Drivage is accomplished by a trip hammer weighing 622.7 Newton falling through a distance of 762 mm, that is 30 inch. First the split spoon is driven 150 into the soil and then number of blows of the hammer required to drive the spoon further 450 into the soil is counted and is described as the N value. Number of blows for each 75 penetration is recorded. For example, 2, 3, 4, 5, 4, 5 giving a N value of 18. It is essential that the bottom of a borehole is carefully cleaned out, removing any loose metal before the test is undertaken. The result obtained from the SPT provide an evaluation of the degree of compaction of cohesionless sands, and the N values may be related to the angle of internal friction and the allowable bearing capacity. Test pits. It is exploratory pit excavated for determining the nature and fitness of ground for engineering works. Test pits with cross-section dimension 1 into 1 to 2 into 3 meter usually are dug by hand labor to explore soil strata. Such pits are helpful to examine the nature of soil and subsoil metal, their contact and soil bedrock contacts, and in some cases groundwater condition. The in situ soil samples are also obtained from these test pits, which could later be tested in the lab. Trench. A long, narrow, shallow excavation in the ground for visual inspection and sampling of the soil. The common dimension of trenches are 1 to 2 meter for hand dug to up to 10 meter for dragline excavator. Test trenches provide a continuous profile of soil strata to observe bedrock contact, structural fissures and defects in bedrock, and obtaining in situ soil samples. Below water table, it is not possible to dig trenches due to high cost of pumping out the groundwater. Adit and shafts. Adits are horizontal or near horizontal passages driven from the surface into the hillside for observing joints, shade joints, falls, solution openings, and other defects. Shafts are the vertical or nearly vertical, circular or rectangular excavation from the surface downward, commonly 90 to 180 centimeter diameter. Shafts are cored or sometimes blasted to the required depth. Core samples. The cylindrical samples the cylindrical sample of rock obtained through the use of hollow drill bit. They are used to determine the subsurface geology and ground condition and bearing capacity. While planning a series of holes, it is possible to determine the altitude, thickness, structure, deformation, and permeability of the rock in the subsurface. Borehole loggings. During drilling, the subsurface materials are collected according to the depth of the drilling. The core obtained during a drillings are recorded in a sheet of paper, graphical representation in a scale according to the depth. This is called the core logging or the borehole logging. During core logging, types of soil, rock, and their different properties are described. Logging charts clearly shows the thickness of individual rock or soil unit and their characters. So this was for today.